For a long time, the thinking was simple. More parameters mean more capacity for a neural network to learn complex patterns. But that comes with a huge problem.
Right. More parameters usually mean exponentially more computation. Training and running models with billions of parameters becomes incredibly expensive, or even impossible. Is there a way to have the best of both worlds? A model with massive capacity, but without needing to activate every single parameter for every single piece of data?
That's exactly the question this paper from 2017 started to answer. They proposed conditional computation, where only relevant parts of the network are active for a given input.
We actually introduced the foundational idea of mixture of experts back in case number TCM-003001. Today we're building on that with a specific powerful variant, the sparsely gated MOE.
So it's not just a mixture anymore where different models chime in. Now we're talking about sparsely gated. What does that sparsely gated part add?
That's an important distinction. Unlike a traditional ensemble where you'd run every model and average their results, sparsely gated MOE only activates a tiny fraction of the total parameters for any given input. It's about conditional computation, not just parallel computation where all models run all the time. The goal is to realize the promise of conditional computation, which this abstract describes as dramatically increasing model capacity without a proportional increase in computation.
That sounds almost too good to be true. How do they manage to increase capacity by so much without blowing up the compute budget?
The core innovation is this sparsely gated mixture of experts layer. Instead of one large network, they have thousands of feed-forward subnetworks, which they call experts.
Thousands of subnetworks? That's a lot. Is each one a complete neural network on its own?
Not exactly a full network, but specialized subcomponents. Crucially, a trainable gating network determines a sparse combination of these experts to use for each example.
So this gating network is like a traffic cop? It decides which specific experts get to work on a particular input?
That's a good analogy for the gating network, but let's dig a bit deeper into the how. Mechanically, for each input token, the gating network takes that token's representation and passes it through a small neural network layer. This layer then outputs a score or probability for each available expert. To ensure sparsity and pick only a few, it typically uses something like a top K operation, selecting the top K experts with the highest scores, and effectively setting the others to 0. For instance, in Mixtral, it consistently selects the top 2 experts. That's a good analogy for the gating network. However, the paper points out there were significant algorithmic and performance challenges to making this work in practice.
So to be clear, we're not talking about replacing a whole neural network with a MOE. It's more like a modular component, a special kind of layer that you can plug into an existing architecture.
Precisely. The sparsely gated mixture of experts layer, or MOE, isn't a standalone model, but a building block. You can swap out a standard feed-forward layer in a transformer, for example, with an MOE layer to introduce this conditional computation. This modularity is key to its adoption.
I can imagine. How do you efficiently manage thousands of subnetworks and make sure the traffic cop actually learns to route effectively?
Addressing those challenges is key. In the next scene, we'll build an intuition for how this sparse routing allows for such colossal models while keeping the compute cost down.
I'm eager to understand the mechanism behind achieving greater than 1000x improvements in model capacity.
Think of it like a massive consulting firm. You have thousands of experts, each specializing in a very niche field. Tax law, mergers, intellectual property, international trade, and so on.
Okay, so when a new client comes in with a problem,
You don't send their case to every single expert in the firm. That would be inefficient.
Exactly. Instead, a senior partner, that's our gating network, quickly assesses the client's problem and internally calculates a relevance score for each specialist. Then it only assigns the task to, say, the top 2 specialists. Crucially, after these specialists process their part, their outputs are often combined, typically as a weighted sum where the weights come from those same relevance scores determined by the gating network.
So the gating network doesn't just pick, it also helps blend their advice based on how relevant it thought they were initially?
Precisely. That's how it ensures a coherent output from the chosen few. The client's problem is the input example, and the specialists are the experts. The senior partner ensures it's a sparse combination. The analogy holds pretty well. Each expert here is a feed-forward subnetwork within the neural network. They're like specialized modules that learn specific patterns.
And the key is sparse. If it wasn't sparse, we'd be back to activating the whole network, which defeats the purpose, right?
Precisely. This sparse activation is what allows the system to claim greater than 1000x improvements in model capacity. We have an enormous number of potential parameters, but only a few are ever active at once.
So it's not just that the model can get bigger, it's that it feels bigger to the input without being bigger computationally. That's a clever trick.
It's a clever trick, but not without its costs. The paper acknowledges only minor losses in computational efficiency. This implies that while capacity explodes, there are still overheads to manage.
I guess the traffic cop isn't free. Routing, sending data to different experts, then combining their results, that must add some computational burden.
And where do these outrageously large models shine? The paper targets language modeling and machine translation, where model capacity is critical.
That makes sense. Language, with its vast complexities and nuances, probably benefits most from having a truly enormous bank of knowledge.
The authors applied this MOE layer within existing architectures. Here, they mention using an MOE with up to 137 billion parameters between stacked LSTM layers.
So the MOE layer itself isn't a whole new neural network from scratch, but rather a plug-and-play component within a larger system like an LSTM-based language model.
Exactly. This initial paper laid the groundwork, but the real challenge was making this approach scalable and practical for modern, even larger models like transformers. That's what we explore next.
I'm curious how they made it work without the minor losses becoming major headaches for models that are orders of magnitude bigger.
Building on that foundational MOE paper, Switch Transformers directly tackles how to scale these ideas. They reiterate that standard models reuse the same parameters for all inputs, while Mixture of Experts defies this.
So the core principle remains: specialization and sparse activation are key, but the earlier MOE models had practical hurdles, as we just discussed.
The authors here explicitly state the problems. Widespread adoption has been hindered by complexity, communication costs, and training instability. These are the headaches preventing MOE from taking off.
Those sound like serious engineering challenges, especially communication costs in distributed training. How does Switch Transformers address them?
They tackled it head-on. The paper focuses on simplify the MOE routing algorithm and design intuitive improved models with reduced communication and computational costs.
Simplifying routing sounds critical. If the traffic cop is too complicated, it adds its own overhead, negating the benefits of sparse activation.
Indeed, a key part of that simplification was introducing a load balancing loss. This is an auxiliary loss function that encourages the gating network to distribute tokens more evenly across all experts, rather than sending everything to just a few favorites. Without it, some experts would be overworked, and others would become dead experts, unused and unable to learn, defeating the purpose of distributed capacity. It's a critical component for stable and efficient training.
So the traffic cop also gets a bonus if it keeps all lanes moving, not just the fastest ones. That makes a lot of sense for preventing those dead experts.
The magic is summarized here. The result is a sparsely activated model with outrageous numbers of parameters, but a constant computational cost.
Constant cost? So regardless of how many trillion parameters the model has, the actual amount of compute for a single input stays the same? That's the holy grail.
Yes, that's the goal. They achieved this by integrating MOE layers into the transformer architecture we know well from cases like TCM 213002, specifically using T5 models.
So they replaced some of the standard feed-forward layers in T5 with these MOE layers, and this led to massive speedups.
Exactly. They report up to 7x increases in pre-training speed with the same computational resources. This means you can train a much larger model faster, or train a model for much longer.
That's a huge practical win. It means researchers can iterate faster or build more powerful models within their existing compute budgets.
Another crucial innovation was enabling large, sparse models to be trained with lower precision, bfloat16 formats. This further reduces memory and compute requirements, especially important for models with trillions of parameters.
Lower precision training can be tricky, often leading to instability. The fact they wrangled that suggests significant engineering effort and further refined training techniques.
These innovations are what truly unlocked MOE for the current generation of massive language models. Let's look at a concrete, recent example of this technology in action with Mixtral.
I'm excited to see how these trillions of parameters actually translate into real-world performance.
The concepts we've discussed today culminate in models like Mixtral. This paper introduces Mixtral 8x7b, a sparse mixture of experts, SMOE language model, which has recently made waves in the AI community.
So Mixtral is a direct descendant of the ideas pioneered by the original MOE paper and refined by Switch Transformers?
Exactly. It takes the core principle of conditional computation and applies it within a modern transformer architecture, building upon the stability and efficiency improvements we just talked about. Mixtral's implementation is quite clear. Each layer is composed of 8 feed-forward blocks, i.e. experts, and for each token, a router network selects 2 experts to process the current state and combine their outputs. This top 2 routing is a specific choice for sparsity.
So every token gets handled by only 2 out of 8 possible specialists in each layer. That's a highly sparse activation.
It is, and this design leads to a staggering efficiency. For example, each token has access to 47B parameters, but only uses 13B active parameters during inference. You get the capacity of a much larger model, but with the computational cost closer to a smaller one. That's the promise delivered.
47 billion parameters available, but only 13 billion actually doing work at any given moment for a single token. That's a huge compute saving.
And the results speak for themselves. Mixtral was trained with a context size of 32K tokens, and it outperforms or matches Llama 2 70B and GPT 3.5 across all evaluated benchmarks. This is remarkable considering its active parameter count is significantly lower than these monolithic models.
Outperforming models that are physically much larger and more expensive to run? That's a strong argument for the MOE approach.
Specifically, Mixtral shines in areas where broad, specialized knowledge is crucial. It vastly outperforms Llama 2 70B on mathematics, code generation, and multilingual benchmarks. This suggests the experts are truly specializing in distinct domains.
So, the MOE architecture isn't just about scaling. It's about enabling a kind of specialized intelligence that performs better in complex, diverse tasks. It's like having a team of experts collaborating, each bringing their specific knowledge to the table.
Exactly. From the theoretical promise of conditional computation to its practical realization in models like Mixtral, the sparsely gated mixture of experts architecture represents a paradigm shift. It allows us to build outrageously large models with unprecedented capacity while remaining computationally efficient by activating only the most relevant parts of the network for each specific task.
And that, Arjun, is how you architect trillion-parameter neural networks that compute like small ones, a truly elegant solution to a fundamental scaling problem.